Hi everybody, I'm going to go through some of the titration multiple choice questions. As always, bear with me, not scripted, and we'll just see how this goes. Okay, we're going to start with question 1. I'm going to go through the information that's at the start of the question first, because as always that's really important. So a student devised an experiment to find the concentration of sulfuric acid in a sample of battery acid. Okay, first of all, battery acid, need to think about that, very strong. And that's going to be giving us implications for safety. So a measuring cylinder was used to transfer 10 centimetres cubed of battery acid to a volumetric flask. Distilled water was added to the volumetric flask until the volume reached 250 centimetres cubed. A 25 centimetre cube sample of diluted acid was transferred from the volumetric flask to a conical flask using a pipette. A few drops of methyl orange indicator were added to the acid in the conical flask before titrating with sodium hydroxide, and then repeated 5 times, but concordant results were not obtained. Okay, now concordant results means within 0.1 centimetres cubed of each other. And then we have a note. Methyl orange is red in acid and yellow in alkali. Okay, so question 1. Which suggestion about rinsing the conical flask between each titration would improve the accuracy of the titrations? So we've got some options here. A, rinsing with acid, B, rinsing with alkali, C, rinsing with water, or D, no rinsing with any liquid. Well, if we think about this question, this is actually just a little bit of AO1 information. That's knowledge and recall about titrations, and it is one of those practical techniques that you need to know about. If we went with A, rinsing with acid, if we add acid to the flask between each titration, then what we're going to be doing is adding acid to the flask. That means that we're adding acid in addition to the battery acid that we're looking at. We'd add acid other than the 10 centimetres cubed that we're adding. That would not be very accurate, so it's not going to be that one. Rinsing with alkali would be exactly the same thing. We would be adding alkali to the flask that then wouldn't be coming out of the burette when we did the titration. C, rinsing with water. Well, rinsing with water between each titration, that is going to be the right thing to do. That means that we're rinsing away any residues, any products from the previous reactant, any unreacted acid or alkali if you didn't do your titration properly. So it is going to be that one. Not rinsing with any liquid is going to be better than A or B, but is definitely not what you should be doing, and you should be rinsing with water between each one. Question 2. Which of these is important in ensuring that the student's experiment is safe? So when it comes to safety, it's important to think through the practical. General safety for titrations would be things like wearing goggles, making sure that you fill your burette below eye level, and that kind of thing. But this is asking about the student's experiment, this particular experiment. And that's something we need to consider when we go through the answers. So A, do the titration in a fume cupboard. Looking at the instructions, is there anything that suggests it's going to be given off fumes? Well, not really. The acid may be slightly fumey, but it is not. Battery acid is just hydrochloric acid normally. It's not going to be something that gives off many nasty fumes. So I would say not that one. B, wear gloves when measuring out the battery acid. Well, what do we know about battery acid? As we said at the start, battery acid is strong. So that one is a possibility. Wash hands before doing the titration. I wouldn't suggest that one's really necessary. And D, carry the burette horizontally when collecting the apparatus. Now that is actually something from the required practical, and carrying the burette horizontally, definitely shouldn't be doing that. That's a definite no-no, because you could walk into somebody, you could break it. Burettes are quite delicate and they're made of glass, so don't do that. So the answer for this one is B. Okay, wearing gloves for the battery acid. We may well put the battery acid in the fume cupboard just to make sure that we're aware of the safety, but it's not necessary. However, gloves definitely is, because it has such a low pH and it is very, very corrosive. Question 3. Which colour change is observed at the end point in each titration? So going back to the instructions, it tells us that we have a colour change, that methyl orange is red in acid and yellow in alkali. Now what they're doing in this experiment is that they're putting the 25 centimetre cube sample into a conical flask. So the acid is in the flask. So that's what we're going to be looking at first. That's where the indicator goes. So the start colour is going to be acidic, which is red. So we're definitely looking at one of these. It has to be either B or D in that case. The next thing we have to think about is, what is the colour change going to be? Well, we're adding alkali to the acid, so it's going to go from being red, and we're going to be adding the alkali gradually. Now we want to get to the end point of the reaction. The end point of the reaction is where we have an equal amount of the acid and the alkali. Now technically that is the equivalence point, but the end point is where we get the colour change of the indicator to indicate that we have got to the equivalence point. Now if we let this go to yellow, that means that we have an excess of alkali, so we don't want it to go yellow. With methyl orange, what we want is the midpoint in between the two, which is actually orange. It makes methyl orange a really useful indicator if you're doing titrations with strong acids. Okay, question 4. Which suggestion would improve the chances of obtaining concordant titers? Now concordant titers, we've already said, is where we get results that are 0.1 centimetres cubed from each other. When you're doing a titration, you need to be getting 2 of those, and you normally need to do that within about 5 tries. That shows you've got good technique. So looking at the answers, the possibilities. A. Invert the volumetric flask several times after adding the distilled water. Now that isn't in the instructions they've given us in the bullet points, however it is part of the required practical for making a standard solution, which is the first part of this required practical for titrations. So that is a possibility. Okay, we'll come back to that in a minute. B. Wash the pipette with distilled water between each titration. Now if we add distilled water to the pipette between we do each titration, remembering that the pipette is being used for the acid, if we add water, we're going to be diluting that acid further. We're going to be changing the concentration of the acid, and that is exactly what they're trying to find out. So we definitely do not want to do that. Definitely not B. C. Add extra drops of indicator to the sample when nearing the end point in each titration. Now again, this is something we don't want to do. Indicators are all weak acids. You need to be consistent with how much indicator you're adding each time. If you add more, then you're adding acid. And even though it's a weak acid, it can change the titration, so we definitely don't want to do that. D. Use a more concentrated solution of sodium hydroxide than the burette. Well, that's definitely not something we want to do, and we'll come back to why that is later in another question. So the answer for this one is A. And the reason why we would need to invert the volumetric flask is because when you make a standard solution, and you've got your volumetric flask, you start off by putting your fairly concentrated solution in the bottom of your flask and then topping it up with water up to your line. Now what happens if you don't invert? Then what you get as you add the water is that that solution gradually becomes less concentrated as you go up. And you can actually see it when you do this, that you end up with it being very pale at the top and very dark at the bottom. When you invert, you put a bong on the top, put your thumb over the top, and you turn it upside down carefully with your thumb up the top a few times, and you can see the mixture all swirling and mixing in with each other. It just means that the mixture is consistent all the way through and that we have the same concentration all the way through as far as possible. And on to question 5. Which suggestion would reduce the overall measurement uncertainty in the titration? Now, uncertainty is a really important part of practical work, and it is one of the ways of checking to see if the practical is as good as it can be. How high is the uncertainty? Now, we have a way of actually calculating measurement uncertainty, and it's expressed as a percentage. The uncertainty is given as a percentage by taking the uncertainty of the equipment, which I'll talk a bit more about in a second, divided by the measurement using the equipment. You times that all by 100 to get the percentage. Now the uncertainty of the equipment is often given by the manufacturer, And it's the manufacturer's way of saying, we've been as careful as possible with making this piece of equipment, but we can't be perfect. Now, it might be that in a volumetric flask, for example, that we're using here, the volumetric flask might have an uncertainty of plus or minus 0.1 centimetres cubed. That's the manufacturer telling you that if you make the solution up properly, you use the right technique, looking at eye level with your meniscus on the line, your 250 centimetres cubed could be 250.1, but it could be 249.9. They're telling you that there is a little bit of leeway with the measurement. So the uncertainty in the measurement that you use is using this calculation that we do. Now, in terms of reducing that uncertainty and making this value go down, there are two things that we can do. We can either decrease the uncertainty of the equipment, but that would involve us using a different piece of equipment, changing the volumetric flask. The other thing we can do is we can increase the measurement. If you make the measurement bigger, you're making the bottom of that fraction bigger, which makes the uncertainty smaller. That's normally the easy way to go. So let's look at the answers. A. Use less concentrated alkali in the burette. So if we use less concentrated alkali in the burette, what would happen to our measurement? Well, if we've got less concentrated alkali, that's fewer moles per volume. So if we've got fewer moles per volume, the volume would increase. And if we're using a burette, that's what we're measuring, the volume. So that is definitely a possibility. And I'd say that's the right answer, but it's always important to go back and double check. So let's have a look at the rest just to make sure we can eliminate those. B. Use phenolphthalein indicator instead of methyl orange. Phenolphthalein indicator we could use for this practical, but it should give us the exact same result, so that shouldn't change anything, definitely wouldn't change the uncertainty. C. Use smaller samples of the diluted acid in each titration. Well, if we use a smaller sample, then what's going to happen to the amount from the burette? That would cause the volume from the burette to go down, and that's the opposite of what we want to happen, so we don't want to use that one. D. Begin each titration with a burette filled to the 0.00 centimetre cubed mark. That doesn't matter, okay? We never have to actually worry about doing that. As long as you know what your start volume is, you don't need to start at 0.00, so it's one of those things we say don't waste your time, even though it looks nice when you start. So the answer to this one is A, as we suspected, but as I said, always make sure that you double check that the others are not possibilities before you go straight away with the first answer. Okay, so question 6 onwards isn't anything to do with the previous questions, so there's no method that we need to worry about for this one. These are kind of standalone. So 25 centimetre cube samples of sodium hydroxide solution were taken by pipette from a beaker. These were then titrated with an aqueous solution of ethanoic acid. The concentration of ethanoic acid calculated from the experimental results was found to be lower than the actual value. Which of these could explain the difference? So, looking at each of these in turn. A. Rinsing the pipette with distilled water before filling with NaOH. So, if we rinse the pipette with distilled water, we're going to be diluting the NaOH. That will lower the concentration of the sodium hydroxide. If we're lowering the concentration of sodium hydroxide, we're going to need less ethanoic acid. That's not going to be the right answer, so we can ignore that one. B. Rinsing the burette with distilled water before filling with ethanoic acid. Well, if we add distilled water to the burette, then we are going to be diluting the ethanoic acid. And as we've just said, diluting is a lower concentration. Well, that's exactly what they're asking for. So I'd say that's the right answer. But as previously, let's double check. C. Rinsing the walls of the conical flask with distilled water during the titration. Now, that's actually good practice. When you're doing a titration, you're doing this in a conical flask, which has sloped sides. Now, the sloped sides help encourage solution to go back into the reagent mixture at the bottom, because as you swirl, what happens is that the solution does go up the sides. So the sloped sides help that. However, what you can do is towards the end point of the reaction, you can do a few drops of distilled water around the edge of the flask just to rinse all of your reagent back into that reaction mixture to make sure that it's not clinging to the sides. Gives you a more accurate result. So that's actually good practice, so C wouldn't cause it to go wrong. D. Rinsing the beaker with distilled water before filling with sodium hydroxide. That is possibly, we generally want to clean the equipment, but that is going to decrease the concentration of sodium hydroxide, but it won't change the number of moles, so that's not really going to be an issue either. So the answer here is B, as we suspected, but again, always make sure you double check and don't just go with your first instincts. Question 7, again, completely unrelated to the first few questions. What is the burette reading for this transparent liquid? So, a few things to remember is that first of all we have a meniscus. That is where the water clings to the side of the burette. It's why water forms a droplet if you put it onto a surface. We have surface tension. So the meniscus here is going down, and you always want to read to the bottom of the meniscus. The other thing is that we need to be looking at the burette at the right angle, and so we want to be looking at the burette at eye level. Bit of a dodgy drawing there, but we want to be reading that at eye level as far as possible. So you want your eye level to be with the bottom of the meniscus. My drawing's a little bit out there, but we'll let me off for that one. Reading this, we're then going to be looking at the divisions. So the divisions here are all 0.1 centimetre cubed, and we're going 24, and then we're reading down to where it is. Again, drawing's a bit dodgy, but that comes out to be 24.3. This is given to 2 decimal places anyway, but if it wasn't, you need to make sure it's to 2 decimal places, but the answer is B. And on to the calculation questions. So these often take a little bit longer than the rest of them. In a multiple choice section of an exam, you get 25 minutes suggested time to do 15 questions. So they do expect that some of the questions are going to take you a little bit longer than others. Calculations often do. So, which of the following would react exactly with a solution containing 0.05 moles of sulfuric acid? First of all, sulfuric acid, H2SO4. Remember your reagent formulae. And what that means is that we have 2 H pluses for every H2SO4 in the solution. So the concentration of H plus, we represent with square brackets, is actually going to be 2 times 0.0500, which is going to be 0.100 moles of H plus. That's important to remember. Next we look at our possible answers. Okay, we have A and B that are both KOH. Now KOH is going to provide 1 OH minus, both of these, whereas we've got for C and D barium hydroxide, and each of these will be giving 2 OH minus because it's BaOH brackets 2. Very important to bear in mind those. So we've been given a volume and a concentration for each of these substances, and if we remember our equations, moles is equal to concentration times volume. So that's what we're going to do. We're going to work through really quickly each of these to work out how many moles of each substance we have, and therefore how many moles of OH minus. Remembering that H plus OH minus reacts in a 1-to-1 ratio when we're doing neutralizations. So for A, the concentration is 1 and the volume is 50 over 1,000, and so we end up with 0.05 moles of KOH, and therefore 0.05 moles of OH minus as well. For B, we've got 2 molar, but we've now got 0.1 decimeters cubed, 100 over 1,000. So we've got 0.2 moles of KOH, therefore 0.2 moles of OH minus. Moving on to C, again we've got 2 molar and we've got 100 centimeters cubed, or 0.1 decimeters cubed, so we have 0.2 moles of barium hydroxide. However, 2 OH minuses for every barium hydroxide, so we actually have 0.4 moles of OH minus for that one. For D, we've got 1 molar and we've got 50 centimeters cubed, or 0.05 decimeters cubed, so we end up with 0.05 moles of barium hydroxide, which is therefore 0.1 moles of OH minus. So we're looking for the 1-to-1 ratio between H plus and OH minus. We've got 0.1 moles of H plus coming from our sulfuric acid, and if we look at D, we have 0.1 moles of OH minus coming from the barium hydroxide, and therefore the answer is D. Okay, question 9. 25 centimetres cubed of ethane dioic acid required 22.5 centimetres cubed of 0.1 mole per decimetre cubed potassium hydroxide for complete neutralisation. And then it's asking you to work out what the concentration of ethane dioic acid is. So first of all, thinking about this, we've got a dioic acid. An ethane dioic acid has this structure. The dioic means that it has two carboxylic acid groups, so that's ethane dioic acid. So we've got two H's that are able to be donated. This is reacting with KOH, okay, potassium hydroxide, which only has one OH minus that it can provide. So the first thing we've got to think about here is what's the ratio that these two are going to react together in? Well, ethane dioic acid and the KOH are going to react together in a 1:2 ratio. We need two KOHs to give us two OH minuses to react with the two H pluses from ethane dioic acid, because remember that H plus plus OH minus always reacts in this 1:1 ratio when we've got neutralisation. So once we've got that figured out, we can move on to look at what information we've been given. So we've got a volume and a concentration for potassium hydroxide, and so that means that we can work out the moles of potassium hydroxide. It's going to be conc times volume, 0.1 times 22.5 over 1,000, remembering to convert from centimetres cubed to decimetres cubed. And so we have 2.25 times 10 to the minus 3 moles of KOH. Taking our ratio into account, the moles of acid is therefore going to be equal to the moles of KOH divided by 2. And so we have 1.125 times 10 to the minus 3 moles of acid. Now in the question we've been given a volume of the acid, we've just worked out moles of acid, and therefore we can work out the concentration. So conc equals moles over volume, that's the concentration of the acid. 1.125 times 10 to the minus 3 divided by the volume, which is 0.025, that's 25 divided by 1,000, and that gives us an answer of 0.045 mole per decimetre cubed, and if we look up, that's B. Okay, and finally question number 10, slightly trickier. I know that this stumped a few people. But again, we'll just approach this as we have with all the others. We're going to read through the question, identifying what information we've got and what they're asking us to do. So, in a titration, 0.52 grams of a diprotic acid reacts exactly with 100 centimetres cubed of 0.1 molar sodium hydroxide. So, what information do we have? We've got here grams, so that's a mass. We've got here diprotic acid, H2X. Okay, so that means that we've got this 1:2 ratio going on just here in the equation. We've got this acid reacting with a volume, 100 centimetres cubed, of sodium hydroxide, which has a concentration of 0.10 molar. So we've been given a mass, a volume and a concentration, and we've got to identify the acid from ethane dioic, propane dioic, butane dioic or pentane dioic. So thinking about the information we've been given, we've got mass, volume and concentration. What equations do we know that link these together? Well, if we're looking at mass, we know that moles equals mass over relative mass. And then we've got volume and concentration, and we should remember that concentration is moles over volume. Now we've got to do some identifying. We're identifying an acid. And handily, they've given us some structures. They've given us names, but we can then work out structures. If we've got structures, we can then work out MR. So ethane dioic, we did on a previous slide. Ethane dioic acid is that. And if we add that up, that has a relative mass of 90. So 12 times 2 plus 4 lots of 16 plus 2 lots of 1. Propane dioic acid has a structure that has 3 carbons, but again with the 2 carboxylic acid groups. I'm not drawing displayed formula here, so I'm just going to do the OHs like that. If we work out the MR of that structure, that has an MR of 104. Butane dioic acid has 4 carbons, which if you add up has a relative mass of 118. And then pentane dioic acid has 5 carbons, and I'm going to leave those as what we call sticks there. If you ever see sticks on a mark scheme, it's where you're lazy and you don't put H's on the end. But if we add up the MR of that, we get 132. So what we then have to do is use the information that we've got to work backwards, as we have done with other calculations, through the information to work out the MR at the end, because that will help us identify, or that will allow us to identify the acid that we've been given. So what information have we got that we can do a calculation with? We've got this volume and concentration information of sodium hydroxide. So the first thing I'm going to do is to work out moles of NaOH by doing concentration times volume, 0.1 times 100 over 1,000, and that comes out to be 0.01 moles of NaOH. Now we've already said that we've got a 2-to-1 ratio, so therefore moles of H2X is going to be moles of NaOH divided by 2, 0.01 divided by 2, so we have 5 times 10 to the minus 3 moles of acid. And that's because of this ratio that we had at the top in the equation that they gave us. Now that we've got the moles of acid, bearing in mind that we have the mass of the acid at the beginning, we can work out the MR. So the MR of the acid is equal to mass over moles. 0.52 grams was the mass given. The moles we've just worked out is 5 times 10 to the minus 3. And if you pop that into your calculator, that comes out to be an MR of 104. Which means the answer is B. As always, if you have any questions about any of the questions, then get in touch.